Hello everybody, hope we're all doing well, hope we're all okay, feeling safe and healthy. So here, this video is for anyone that missed school on the 19th and 20th. We're going to go over the content that we covered then, just to get you caught up, because you can't go to extra help or anything right now. As we're working through this video, I'm going to be going through a slide presentation that I shared in the same post on Google Classroom, so you can follow along with me so you know which slide I'm talking in reference to, because I can't write all that information down here. It'll take a lot of time, and I'll leave that slide presentation up so you can take notes from it as we go. We're going to continue with our talk on exponential functions. We began talking about them a little bit. Exponential functions are really going to be one of the first nonlinear functions that we spend a lot of time on. I believe you spent time on quadratics last year, spent a little bit of time on them, but we're really going to dive into exponential, so this will be the first nonlinear function that we really get a lot of depth into with. So on the first slide of that presentation, and feel free to pause this video as we go, in case you want to take notes down, whatever you want to do, the video you can pause and start up whenever you need to. On the first slide, should be notes that we already have. This slide says y equals a times b to the x, and this was just the form of an exponential function. And of course, we had b was not equal to 1, and a was not equal to 0, and we knew that b was also greater than 0. We had a positive number for b. And I believe the first problem we talked about with this was, I believe it was Ed had, I think it was 12 pennies, and he was doubling the amount of pennies, and we wanted to create a function to represent that, and we successfully got to 12 times 2 to the x. He started with 12, and he kept on doubling every week. So x was weeks, y was total amount of pennies, so the number of weeks was how many times he was doubling. Perfect example of an exponential function. And we're going to go into more detail with these. We're going to talk about how to graph these and special parts of the graph. We did a little bit of graphing with them. I believe we defined what an asymptote was, and we talked about exponential growth versus exponential decay, but we didn't get in a lot of detail of how to tell if something's a growth or a decay. We just defined what they were, and that we knew that there was two types of exponentials there. So we're going to get into a little more detail with that here. So we have, I'm on slide 2 now. So slide 2 says y equals 2 to the x minus 3. Let me look for a better marker. So 2 to the x minus 3, and we are told to create a table, to graph the function, to state the domain and range. So we need a table. I did not bring home a graphing whiteboard, so we're going to have to make do with here. So we're going to graph. I'll make a little coordinate plane. We also want to state the domain, we want to state the range, so we'll keep that in mind. So let's start with our table. Shouldn't need all this space. And we decided these were good values to use, good inputs, -2, -1, 0, 1, and 2. These might change based upon the function we have. We'll look for certain things, but for now we'll use them. They're great for this function. And when you're substituting in, be really careful with the negative values that you substitute in, because they're not going to change your base, it's not going to make it negative, but it will turn it into that fraction where it's going to go in the denominator. So be really careful with that. So we're going to start with those negative values. 2 to the -2 minus 3. When we substitute that in, well, 2 to the -2 is 1 over 2 squared minus 3, and that becomes, sorry range, you're going away. Ooh. That becomes 1/4 minus 3, which becomes -2 3/4. I'm going to leave it as a mixed number. I know normally I say leave improper fractions. I like improper fractions, but to help us recognize something, we'll leave it as the mixed number. We'll do 2 to the -1 minus 3 as our next input here, which is equal to 1 over 2 to the first, which is 1/2 minus 3, and we should end up with -2 1/2. Then we have 2 to the 0 minus 3. 2 to the 0 is 1 minus 3. We should get negative 2. 2 to the first minus 3. Well, that's just 2 minus 3. So we should have negative 1. And 2 squared minus 3. We get a nice 4 minus 3, which should give us a positive 1. So these are our outputs for our given inputs here. And we are going to now graph this on the coordinate plane. We'll bring the range back. So on the coordinate plane, let's make a nice coordinate plane here. So if you have graph paper, that would be great for you. For me, that is not the case. So we're going to count by ones on our graph. 1, 2, 3. I should be fine with just 3 spaces. So when we graph, we're going to have the first point 2, 1, 2, 1. We're going to graph 1, negative 1. That puts us right here. 0, negative 2. 0, negative 2. Negative 1, negative 2.5. Negative 1, negative 1, 2.5. Negative 2, negative 1, 2, and 3/4. So here's negative 3 with 3/4 about right here. If we were to continue this pattern, or look for a pattern here, if we were to continue and we were to say x is negative 3, x is negative 3, our y would be 1 over 2 to the third minus 3. So 1/8 minus 3, which is negative 2 7/8. If we did negative 4, we would have 1 over 2 to the fourth minus 3, which is 1 over 16 minus 3, which is negative 2 15/16. Notice a few things actually you can notice. Your denominators go 2, 4, 8, 16. Those are your 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, well 2 to the negative of all those because you're in the denominator, which is what we had. But notice how you're going to get really, really close to negative 3 for your output, but you're never going to get there. The only way you could get there was in your function would be if 2 to the x somehow equaled negative 3, or if somehow equaled 3, sorry. If this equaled, somehow equaled 0. If 2 to the x equals 0, and you subtract 3, then you'll equal negative 3. And this will never equal 0. We cannot get this to equal 0. So that's going to make it impossible to get a value of negative 3. We can get infinitely close to negative 3, and in fact we will get closer and closer and closer the further we go, but we're never going to touch that negative 3, which is what we defined, I believe on Tuesday, as an asymptote. A line that you will approach, but you'll never touch. We have one of those here at y equals negative 3. Exponential functions have asymptotes. So we're going to get infinitely close, but we're never going to quite touch. So your graph would look something like this. We're going to get infinitely close to y equals negative 3, but we'll never touch it. Now in an exponential, I mean it's really flat over here. Not exactly flat, but kind of approaching, has a look similar to being flat. And the main behavior of the graph is like right here. It's where it really starts to change. And then it goes up exponentially and starts to increase at a rapid pace. So this is the part of the graph you really want to show with an exponential. Because to the left, it's kind of just going to look straight across. All the way to the right, you're just going to be going straight up and down. Here's where the change in the graph is really taking place. It's the really significant part of the graph. And we need to state our domain, our range. So our domain, all of your possible x values, put the domain right down here. Our domain is, well, it's all values x such that x can go anything to the left and x can go anything to the right. So x could be any number that exists in the set of real numbers. Our range is going to be all values y, and we're never going to be below y for this graph. We are above, or sorry, we're never going to be below y equals negative 3, but we are above y equals negative 3. We never are going to touch it though. So y is anything that's greater than negative 3. There's your range. And we have an asymptote at, well, that was at y equals negative 3. So there was our first graph that we did, and this would actually be classified as an exponential growth function. And we can tell that by simply looking at the equation. So I'm going to move on to slide 3. looking at the equation in slide 3, it defines an exponential growth. Y equals a to the xb, and a is greater than 0. B is going to be greater than 1. Any number that's being raised to the x in the exponential, that's your b, if that's greater than 1, it's going to be a growth. The function's going to go up as you go from left to right. As your numbers get larger, you're going to become larger because you're multiplying by a number greater than 1 over and over and over and over again, making you greater. You multiply by anything greater than 1 repeatedly, it's going to increase or grow for an exponential growth. So that's what you're looking for. If you see this, your base being raised to the x power is greater than 1, you're going to have a growth function. And you can stop and take those notes down if you want. I'm going to move on to the next slide. Our next slide was y equals 2 times 1/2 to the x. Your a value is 2, your b value is 1/2, and you're being raised to the x. That's what indicates you have an exponential function here. And it says make a table and graph the function. So we'll make a table again, and we're going to graph x, y. We'll make a nice graph. We're still going to stick with these values for now. We're going to talk about when we should choose other values. So let's go ahead and substitute 2 times 1/2 to the negative 2. So when we have 1/2 to the negative 2, that's going to make it 2 times, well, the negative is going to take your reciprocal, so it's going to be 2 times 2 squared, which equals 2 squared is 4 times 2 is 8. 2 times 1/2 to the negative 1, well, that's going to take your reciprocal. 2 times 2 to the 1, so 2 to the first power is 2. 2 times 2 is 4. There's your output. 2 times 1/2 to the 0th, anything to the 0th is going to be 1. Anything besides 0 to the 0th is going to be 1. 2 times 1 gives you 2. Now we're on to 2 times 1/2 to the positive first power, which becomes 2 times 1/2. 2 times 1/2 is 1, so we have 1. And then 2 times 1/2 squared equals 2 times 1/4, which should equal 1/2. So here's your outputs for the given input. They all go together. We have coordinates here to graph now. Give us our behavior of the graph. We have our y, we have our x. And let's graph in, let's go in black. We're going to count by, we need to get up to 8. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So we're going to graph. -2, +8. -2, +8. -1, +4. -1, 4. 0, 2. 1, 1. And 2.5. If we were to continue this, you might see a pattern going on. Maybe not yet. If you were to go to the third power, 2 times 1/2 to the third would be 2 times 1/8, which is equal to our 1/4 here. If you were to continue, 2 times 1/2 to the 4th equals 2 times 1/16, which is 1/8. You might notice we're going to approach 0 and never get to 0. We have an asymptote at 0. So, asymptote at 0, and our function looks like this on our graph. Our asymptote's at 0. Let's indicate that. We'll draw a nice little dotted line here. Y equals 0. There we have an asymptote at 0. You might notice in this function has a different shape. If you look at your equation, your b value is not greater than 1, it's actually less than 1. That's going to indicate a different type of function. this would represent a decay function. So when your b value is less than 0, we're going to have a decay. And that's on slide 5 now. So again, you have y equals ab to the x. A is greater than 0. Now if b is less than 1, but still greater than 0, so it's those numbers 1/2, 1/4, 1/8, it could be anything greater than 1, or sorry, less than 1, but greater than 0, then you're going to have a decay function. Decay functions get smaller as you go from left to right. They go down as you go from left to right, because you're repeatedly multiplying by a number less than 1. So like you're multiplying by a half over and over, you keep taking a half of something, you're going to get smaller and smaller and smaller. So that's why it's called a decay function. Alright, let's look at some other ones. So if you weren't here on Thursday and Friday, you might have seen those. I don't know if we did those or not, but these I know you definitely did not see. So we're on to slide number 6 here, and we have the function y equals 4 to the x minus 2. And we talked on Thursday about this being, or having a transformation to it. So this is actually going to shift the graph a little bit, and it's going to shift it left or right. And we're going to have to choose different inputs for this. Now, in order to choose our inputs, it's good to think about, I'm going to draw an exponential like this. For an exponential, the part of the graph that you really want to get on the graph, the part that you want to have like coordinates for, is like right here. It's like this part of the graph. It's where you really start to go from this, not flat, but resembling flat, and you really start to change. This is like the big important part of the graph. You want to get this graphed. Otherwise, if you graph this left side, your graph will look like this if you have the wrong values. And that's not really showing the shape of the exponential. If you graph all the way to the right, after you see that turn, your graph is just going to go up. It's not really showing the shape of the exponential. You want to get where you go from like that flat to the higher rate here, where things have gone up exponentially and they're really starting to take off. So in order to do that, the way I like to think about it is, in the end, our base is 4. We're going to want to raise 4 to the, we're going to want to do 4 to the negative second, 4 to the negative first, 4 to the 0, 4 to the first, 4 to the second. These powers are going to really have us see where that graph takes off. But if we were to put, let's say, -2 in here, you would have 4 to the -2 minus 2, you'd have 4 to the -4. And that's going to be kind of further to the left of the graph. And it's going to be more of that flat part. So in order to get the right values, we need to shift everything by 2. And to make up for that, we're going to have to add 2 for each value here. So instead of -2, I'm going to have 0. Instead of -1, I'll put 1. Then 2, 3, and 4. I shifted everything by 2 for our inputs, because now when we substitute in, we have 4 to the 0 minus 2. It's going to be 4 to the -2. So it's like taken to the negative second power. Put 1/16. That's our first output, 1/16. And then, actually we have 4 to the 1 minus 2. It's going to be 4 to the -1. Then we're going to have, hopefully, 1/4. Then we'll have 4 to the 2 minus 2, which is 4 to the 0th, which is 1. 4 to the 3 minus 2, which is 4. And 4 to the 4 minus 2, which is 4 squared, which is positive 16. So positive 16 is our final value. We should have been able to tell right from the beginning that this is a growth function. 4 makes it a growth. So our graph, we should expect a graph that looks like this. Let's go ahead and make a coordinate plane. Actually, let's shift this a little bit, because I'm going to need positive values. Let's do it like this. So y, x, and let's go ahead and graph. So we're going to start at 0 for x and 1/16. 1, oh, we gotta count actually. Let's get some counting first. We need to go all the way up to 16 for 4. 4, 5, I'm going to go up to 8. And we're going to have to estimate that last point. So 0, 1/16. 1, 1/4. Looks closer to 1/2, but we're doing our best. 2, we're at 1. 3, we're at 2, 4. And then 4, we're at 16. This was 8, so 16, hopefully you can still see, is up here. We've really taken off. So now we have this part of the graph where you really start to see the change. And yeah, there we go. There's our graph. We're going to have an asymptote at 0. And I don't know if we've noticed the pattern for recognizing the asymptote in the equation. But in your equation, you have, we'll say y equals ab to the x, and we'll say plus h at the end. And your plus h is going to be your asymptote. Here we have plus 0, so you can have an asymptote at 0. If we had, like in our problem 2 problems ago, we had -3, we had an asymptote at -3. So that's going to really be a huge indicator for us. And we'll look into that in a little bit. But here's our graph. We want to state our domain. Our domain is all values x, such that x is a real number. And our range is going to be all values of y, such that y is greater than 0. And we have an asymptote at y equals 0. And this is a clear growth function. But that -2 up there, that shifted our points a little bit. The whole graph kind of shifts 2 units to the right if it was just 4 to the x. That's what that -2 is doing for us. So we adjusted our inputs so we can make sure we're graphing that, this part of the graph where we see the behavior really start to change. Alright, we're going to move on to slide number, what are we on? We're on 7 now. We'll do 7, 8, and 9, and then we'll stop. So slide 7, we have, let's see, we have y equals 1/2 x plus 1 minus 2. So just from looking at this, some things we should recognize. Your base being raised to the, in this case, x plus 1 power, but your b is going to make it a decay function. It's less than 1, so we're decaying. We should know, recognize here, we're going to have an asymptote at y equals -2. That's what -2 is going to tell us. And this little plus 1 is going to tell us to choose our inputs a little bit differently. The whole graph is actually going to shift 1 unit to the left. So let's choose some values. Again, I like to think of it like what values you're going to put in so you end up raising in the end to the -2nd, -1st, 0, 1st, and 2nd power. And if you put, let's say, 2 in here, you're going to go 2 to the 3rd, which is a little higher than what we wanted. So you're going to have to subtract 1 from everything. So instead of -2, we're going to have -3. Instead of -1, we'll have -2, so on and so forth. We'll end at +1. So when we put -3 into here, we're going to have 1/2, -3 plus 1 is to the -2 minus 2. -2 to the -2 is going to give us 4 minus 2. That's going to make us have an output of 2. 1/2 to the negative, you put -2 in here, you're going to end up with -1 minus 2. This ends up being 2 minus 2, which gives us a nice 0. 1/2 to the, you put -1 in the function, you're going to end up with a 0 up here. So we're going to end up with 1 minus 2, which is -1. 1/2 to the 0 plus 1, so it's 1/2 to the 1, or first, which ends up being 1/2 minus 2, so 1/2 minus 2 is negative. I'll leave it as a mixed number, -1.5. And then we're going to have 1/2 to the 2nd power minus 2, and that's because when you put 1 in, it'll be 1 plus 1, giving you the 2. So it's 1/4 minus 2, which is -1 3/4. You might recognize the pattern here. It looks like we're approaching -2, but we'll never get there. There's that -2 popping up. So let's go ahead and graph. let's make a nice coordinate plane. Here's our y and our x, and we're going -3, 2, 1, 0, 1, 2. And we'll go 1, 2, 1, 2. There's our graph. So let's go in red here. -3, we're at +2. -2, we're at 0. -1, we're at -1. At 0, we're at -1.5. And at 1, we're at -1 3/4. Notice the shape of a decay function. Like I said right in the beginning, we should have a asymptote at y equals -2. So let's go ahead and show the decay exponential. Ooh, that should approach but never touch. This would be our graph for y equals 1/2 to the x plus 1 minus 2. And if we want to state our domain, again, domain is going to be all values of x such that x is an element of the real numbers. And our range is going to be all values of y such that, well, y can be anything that's larger than -2. Because we approach the line y equals -2, but we never quite touch it. That's why it's called that's why it's an asymptote there. Okay, that was slide number 7. So if you're feeling okay with this, then by all means you don't have to keep going, but if you're not feeling okay, we'll do one more and then we'll break down the equation a little bit. So I'm on slide number 8 here. Actually, if you're feeling okay with this, you still should probably say for slide 8, because it does show us another type of transformation. So I take that back, I apologize. We have y equals 2 to the, or y equals -3 times 2 to the x plus 4. Now some of the things we should notice, should be expecting an asymptote at +4, y equals 4. It should be resemble a growth function, but we have a that with a negative. And we actually said a should be greater than 0, but we're going to see what happens with that negative and how it resembles a growth function. So we're going to be a little careful with what we do, make sure we have everything correct, and we'll see what this does to the graph. We're going to make a table and a graph for the function. So, x and y, there's no little adjustment up here in the exponents, so we'll use those -2, -1, 0, 1, and 2. And let's start with -2. -3 times 2 to the -2 is going to end up being 1/4. And then plus 4. So we're going to end up with -3/4 plus, if you want to do a little math there, 16/4 you can do. Or actually, we want to keep it as a mixed number, so plus 4. So we're going to end up with 3 and a 4th. Then when we have -1, -3 times 1/2, 2 to the -1 is 1/2, plus 4, we'll have -3/2 plus 4. So then here we have +2 and a half. When you add -3/2 to 4, you get 2.5. -3 times 2 to the 0th is 1, plus 4, that's -3 plus 4 should give us 1. -3 times 2 to the first power is 2, plus 4 equals, well, that's -6, plus 4 is -2. And lastly, we have -3 times 2 to the second power, which is 4, plus 4, so -12 plus 4 gives us a -8. And let's see how this graph looks, and we can see what that negative sign did for us. So let's make a nice coordinate plane. And here we are, here's your y, here's your x. We'll count by 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4. You have to estimate this first point. So at 2, we're at -8. So that was 5, 6, 7, 8. -1, -2. 0, you're at +1. Then at -1, you're at 2.5. 1, 2.5. Then at -2, you're at 3 1/4. Kind of tough to tell. My graph is a little off. This point should probably be closer to right here. But hopefully you're using graph paper and you can see. Well, let's first get the asymptote, +4. So our asymptote should be, ooh, I missed that by a little bit. Should be right here. We'll say that's y equals 4. And we're going to approach 4 but never quite get there. Hopefully we can see that's the pattern here. My graph is a little off. So this is what the negative sign does. If the negative sign wasn't there, we would say this was a growth function, which would look like this. Growth function generally has a shape like this. So the negative reflects our graph over. It resembles the reflection of a growth function. That's what the negative is going to do. Same asymptote though, we didn't have to shift left or right, but it resembles the growth function because that negative flips you down, reflects you over the asymptote. So our domain and range for this, domain, well, it's still all values of x, such that x is an element of the real numbers. And y, well, y can be anything, so long as it's less than +4. We're going to approach +4, but we're never going to touch +4. Okay. So our last slide, it's really just breaking down that equation, what we should be looking for in the equation. So our last slide, it just says, what does the equation tell